Well, good morning from sunny California. I'm at the University of California campus in Davis. I'm Glen Fox, Professor of Malting and Brewing Science, and I'm looking forward to presenting some information to you today about some areas of research we're involved in, but not just us, others are digging deeper into malt quality, and we're moving away from a content paradigm more to a malt composition paradigm because we know how much malt contributes to beer. We measure a few things in malt, but there's a lot more to it than what we measure. So the example I've got here is 3 different malts, and they vary quite differently in quality. We might talk, is it quality malt or is it malt quality? Well, hopefully it's both. You do get some quality malt, but we have to measure malt quality. And most of those parameters are the usual things we measure. I know that for maltsters, it's important we use these to understand the quality that we've produced. But for a lot of brewers, they might not necessarily know what all these things mean to them. And honestly, very few of these are used in brewhouse calculations. But it does always give us a guide of what the malt quality should be like. We've all heard about this, malt is the soul of beer, and I was reading some old documents, and we think that the first ever reference to this particular phrase, malt is the soul of beer, was in about the 1870s. And it's been used ever since. And really, how can we actually have beer without malt? What does malt bring to beer? Well, other than some obvious things like color and flavor, it brings the fermentable sugars, the amino acids that are required in fermentation, numerous proteins and peptides, and lots of other flavored compounds that we don't measure, but we know they're there when we know they're important. Malting is a modification process. So the malting process itself is really just a modified germination process. And maltsters deliberately control the germination and the drying of the germination, but it's really just modifying the internal components, modifying the endosperm, breaking down the major substrates, beta-glucan, arabinoxylan, and protein. Ideally, we don't want to modify too much starch. We're saving that for mashing. So we're really targeting the breakdown of storage protein and the beta-glucan and arabinoxylan that are building up the cell walls, the endosperm cell walls. Obviously, there's difference between malt quality. We have ale malts and lager malts, and that's often to do with the degree of modification we give the grain, but also the level of enzymes that some of these grains will have as well. So there are different ways we can produce these different malts, and we would use different malts for different brewing products. I'll focus mainly on proteins because this is an area that probably hasn't had as much attention. If we talk about malt quality, well, so much work has been done on starch degrading enzymes, so much work on the enzymes themselves, a bit more work on the substrate, the starch itself. There's been a lot of work done on beta-glucan and understanding the effect of beta-glucan on wort, runoff, filtration. Less so on arabinoxylan, but it's probably just as important as beta-glucan. But the one that's probably missed out most, but we need to pay most attention to, is the protein modification. Now, in the modification process, we're talking about hundreds of proteins. And it might surprise people that when we actually do measure all the proteins in malt, we are talking hundreds and hundreds and hundreds of individual proteins. A lot of these are specific enzymes. Most of these are carried over from grain fill. So when the barley or the wheat is growing in the field, a lot of the proteins are left over from that grain filling process. Now, we understand that the classification of proteins fits into solubility groups. Are they water soluble? Are they alcohol soluble? But they're also now classified into functionality groups. Are they metabolic proteins? Are they protective proteins? And we talk about storage proteins. Now, the balance between these is very different. The storage proteins make up about 30 to 40% of total protein. And yet there's about 10 of these individual proteins. The other 400 or 500 proteins fit into this metabolic and protective class. So it's a real imbalance between the total amount and the functionality or the composition. And this is where we're trying to unravel this a bit more and understand how some of these proteins are more important, some are less important when it comes to making malt and brewing. Now, if I talk about enzymes, I think most people might understand the basics of enzymology. It's basically what we talk about, the lock and key function. So the substrate is a large molecule, and the enzymes will be normally small proteins that come and do something specific to that substrate. They might cut as part of the substrate into pieces, and the great example is beta amylase cutting maltose off starch chains. So the substrate is starch, beta amylase is the enzyme, and it just cuts maltose off the end of the chain and produces that sugar. It then releases itself from the starch, and it'll then bind to another part of the starch chain to produce maltose. So this is the basic thing. We have a substrate, we have enzymes, and we produce products. And this is an ongoing cycle during malting and definitely during mashing and fermentation. The purpose of malting really is to modify the internal components. There are many, many enzyme groups, but we talk about mainly the starch-degrading proteins, proteases that degrade protein. There are enzymes that degrade lipids, polyphenols. All of these others have specific enzymes that will degrade those. The interesting thing is when we talk about malt quality, we might talk about one of these things. We might talk about protein content, or we might talk about starch-degrading enzymes, DP or alpha amylase, but we never talk about the totality of this enzyme system. And this is sometimes where we're missing out on important information that will definitely impact on brewing process. We rarely measure fermentable sugars, and I personally love to know how much maltose and glucose I've got in my wort before I pitch my yeast. So I'll sort of harp on about this protein modification process. So that's an SEM of basically an internal component of the endosperm. These large spherical bodies are starch granules, whereas that sort of netted matrix is actually the storage protein. So that's what we're trying to hydrolyze during malting. And depending on how well modified we malt, was really how much of that storage protein we break down. Now, the interesting thing is we actually have proteases to do this. They're designed perfectly by Mother Nature to do this. There's 4 classes of these proteases, but within each class, there's a number of proteases themselves. So this is one area where, as biochemists, we're yet to really crack how we can come up with an all-encompassing assay for proteases, because they all have very different substrates and different functions. So this is an area of research that really does require more input over the next few years, and I think it will be important for us to understand this more about modification. We understand about non-starch polysaccharides, specifically beta-glucan and ribinoxylan, the function they serve in the endosperm cell wall and the alurone cell walls. They're much more to do with structural impacts. They have specific enzymes, again, that hydrolyze those, beta-glucanase and xylanase. But again, we rarely measure beta-glucanase. We will measure the wort beta-glucan that's left over from malting. But again, this might be an area we need to focus more on measuring the enzyme. And we now have a method we can measure the enzyme itself as well as the substrate. So again, I'm harping on this substrate-enzyme interaction to really understand the relationship between both of those and the product, rather than just measuring one and sometimes none of those. So we'll be familiar with the malting process. It's just a steeping, germination, and drying process. This is a very natural process. We're basically tricking the grain into think it's growing into a new plant. It's been planted in the soil and it will grow a new plant. The chemistry, the biochemistry is identical when we're growing barley in the field as to doing germination in the malt house. But after 4 or 5 days, we'll actually dry the grain, conserving those enzymes and as well as inducing colour and flavour. So this is a very specific process. What changes during the malting process? So we see a small decrease in starch content, and I'll talk a little bit about that, how that impacts on mashing efficiency. We see virtually no change in protein content, but we see a huge change in composition, with hundreds of enzymes being expressed during germination. So overall total protein won't change, but the profile of those individual proteins, those hundreds of proteins, will change. We're looking for a large decrease in non-starch polysaccharides, arabinoxylan and beta-glucan. And again, we don't measure arabinoxylan, and we probably should do that. But again, it's just more work, more cost, more time. We see a little change in the polyphenols. We see some change in the lipids. And we see virtually no change in vitamins and minerals, but I haven't listed those there. anyway. I will briefly mention starch functionality because this is where we are going to get our fermentable sugars from for fermentation. And we know that starch is the most abundant component in grain itself. Doesn't matter which grain, barley, wheat, sorghum, rice, starch is the most abundant component. And starch, the properties of starch give it a characteristic that it'll melt. The starch will melt at certain temperatures, and we call that the gelatinization temperature. We're looking for that in mashing. We're wanting the starch to become solubilized so the enzymes can act on the starch to produce fermentable sugars. We're finding in recent years that the gelatinization temperatures are going beyond what we'd see in mashing. So I was measuring some malt the other day and I had a gelatinization temperature of 68 degrees Celsius. Well, I'm pretty sure there's no brewers mashing in at 68 degrees Celsius, and you'd have virtually no enzymes surviving mashing in at 68. So we're seeing we're trying to work out how we can actually use this information, gelatinization data, to give brewers a heads up on potentially you'll have some problematic malt. Maybe you need to alter your mashing conditions a little bit to sort of get through this. We also know that the malting process will increase gelatinization temperature. So if you've got barley at a gelatinization temperature of 63 degrees Celsius, the malt from that barley will be at about 64 degrees Celsius, and that's changes in some of the starch properties in malting. So we know that this is happening, but I'm not going to focus so much on starch, but it's an important thing, and this is where sometimes when fermentation doesn't go to plan, maybe, just maybe, it's to do with starch gelatinization. On the left is a fairly long list of parameters that most brewers would be interested in. And on the right is our table. And you can see that very few of the parameters on our table actually line up with what a brewer might consider important. So we've got to find a middle ground. And this is where we are at the moment. The maltsters do an amazing job. It's a lot of hard work making malt and testing malt quality. We know most of those things are a good indication of potential malt performance, but there's lots of things we're not measuring that maybe could be measured, but again, time, cost really does prohibit a lot of this. One of the other things about measuring malt quality is how the methodologies we use. So both the methods we use to measure malt quality are based on lab methods more than 100 years old. So we think the first Congress method, so when we measure standard malt analysis based on a European Brewing Congress method, we think it's the early 1800s this method was first proposed. So it's been around a long time. We know what it does. We know how it works. It's a stepwise mash, very similar to a decoction style brew. It allows different enzyme groups to be active, so we can actually continue to hydrolyze those substrates from malting. So this is where poorly modified malts or under-modified malts can actually look better, because in this Congress mash, these enzymes can work on the substrates. The Institute of Brewing was developed in the 1880s, and it's been around not quite as long as the Congress mash, but again, it's important because it is mashing at 65 degrees. So it gives virtually none of those enzymes time to continue to act. So for a lot of ale-style brewing, we need a much better, well-modified malt. So we're looking for Kolbach indexes of well over 42, maybe 44. Whereas for a lager malt, we might even get away with 38 Kolbach. So these enzymes can continue to do their job. So that's the big difference we see. 99% of malt COAs, if you're using a malt COA, are using the Congress method, and it may be atypical for your brewing style. So this is where things can come a little bit unraveled. Again, our key enzymes focusing on producing fermentable sugars are the starch degrading enzymes, and they're really quite inactive at 65 degrees Celsius. So when you're mashing in at high temperatures, you really only have a limited time for beta amylase to work, a little bit longer for alpha amylase to work. Once these enzymes basically become inactive at high temperatures, you will get no more fermentable sugars. So don't think you're going to be getting an increase in fermentables the whole time during mashing. There is a window that these enzymes function, and after a certain period of time, a certain temperature, those enzymes are inactive. Understanding gelatinization may well help that. The relationship between individual proteins and starch content or fermentable sugars, We know that these on the left are our main storage proteins. So earlier I talked about the 10 or so individual storage proteins. These are some of these here, the hordenes, A, B, C, and D, and some high molecular weight glutennins. We can see that generally they're all negatively correlated to fermentable sugars. So that's one reason why we have a protein window. We don't go super high for protein content for malting barley, because as soon as you have high protein content, you'll have low starch and then potentially lower fermentable sugars. So we know there's this relationship between protein and other components. This is where we first start to look at the individual proteins. We measure free amino nitrogen. We don't measure individual amino acids. This can be, again, a little bit misleading on how the yeast can assimilate the amino acids and how efficient fermentation is. But generally, most of the amino acids will be assimilated within 3 days of fermentation, and then the yeast can manage its own nitrogen source after that. We have found some yeast that can assimilate proline, but in general, most yeasts won't assimilate proline. So that's sort of a broad overview of the content, things we focus on. Let's dive a little bit into composition. And this is where this omics revolution is really starting to take hold and create a good footprint in our industry. A number of labs, including my lab around the US and around the world, are working on one or more of these particular technologies: proteomics, metabolomics, and lipidomics. I'll focus mainly on proteomics and some of the work we've done here. But this technology is still at a very limited use because it's very costly to have the technology. It takes time to run the analysis. We put samples in for analysis, and maybe 3 or 4 weeks later we get data back. Well, no maltster can wait that long and no brewer can wait that long. So again, this technology is not quite at the interface for day-to-day use in our industry, but it's still helping us understand what we need. So we can go through the history of the protein methods back to Keldar working in Carlsberg, and then Dumas developed his method. And then we could actually start to separate proteins based on either molecular weight or charge. So the examples of one-dimensional electrophoresis or two-dimensional electrophoresis, probably from the 1960s with 1D, 1970s and 80s for two-dimensional, and then proteomics has sort of really come into its own in the early 2000s. And now it's a fairly standard technology used on research projects. What it does is now allows us to unravel what might have been considered 4 solubility groups or 4 functionality groups into dozens of individual protein functions. So this is an example of some malt. We can actually sort of put these pie charts together and say, what's the proportion of all these different protein functions? Now, 99% of these proteins are not necessarily important in malting and brewing. All of these are left over either from the growing of the barley or the wheat or through some sort of metabolic process of germination. We know there's probably a dozen or so important proteins in brewing, and we're just trying to understand, well, are some of these other ones important, but we haven't been able to characterize those, or they're just passengers. They're with us during the whole process and we can't do much about it. But they're there. And we now talk about in the order of more than 1,000 proteins in beer, 1,000 individual proteins in beer. So for the malt proteome, we've done analysis and we can just see the changes from the barley itself and the individual changes in proteins. And this is a particular experiment where we looked at changes during the malting process right through to kilning, and we see a total of 600 individual proteins. Which ones do we measure? I don't know yet. We're still trying to work out what's going to be the most targeted proteins we should think about. What's the value in that? Who can use that? We try and keep it real. We could get really ambitious and say we need to have 50 different proteins measured. I think that's a little bit out of reach at the moment. But at least it's helping us understand what's going on and what proteins may be more or less important. One of the things about proteomics I do like is we can now actually understand this relationship between the substrate and the proteases. So this is the changes in the increase in the proteases, 3 particular proteases there, 2 cysteine proteases and a aspartate protease. That's on the left. And on the right is actually the storage protein itself. So we can actually now see changes in the enzymes that hydrolyze our storage protein in malting and a loss of that storage protein. So this is now allowing us to really start to visualize this substrate enzyme interaction. And this is where I think proteomics will help us in our industry more, is understand this relationship between a substrate or a protein substrate and enzymes, which are proteins. And I think this is really going to help us understand modification more. It does help us also, if I can sort of move up the process chain a little bit and actually into the brewery, we can actually see changes in individual proteins during brewing. So this is for a couple of hours up to the boil stage. We can actually see increases in some protein abundance, generally a decrease in protein, because the hotter you get, proteins start to denature. The other thing, we can actually see differences between types. So on the left, we have barley malt that's been mashed, and on the right is another grain. I won't mention the grain, but on the y-axis, we can see proportional differences. So there's tenfold more of these proteins in barley than there is in this other grain. And this is helping us understand, potentially, if we use other grains, which proteins don't we have enough of, or which proteins do we have enough of, but we need to sort of upregulate or downregulate some expression. So it also allows us to see and compare different types of grains, different types of malts. And we just completed a large proteomic study of beer itself. This is the pilot brewery at UC Davis. It is truly one of the best pilot facilities in the US, and that's not a pat on the back for us. Honestly, it is. And Kelly, one of my brewers, is hiding in there. You can never get Kelly to stand still in front of a camera. She hates it. But we brewed a standard Aggie ale, because the Aggies are the UC Davis logo. We used this control beer along with Heineken, and it went around the world to 60 different labs. We've had data come back, and they're all doing proteomics on that. In addition, the labs were getting a couple of local beers themselves. So we've had over 100 beers to get proteomics analysis on. It's the largest ever study done. This is going to be a lot more time in cleaning the data and actually analysing the data. So that's basically the flow diagram. I'll skip straight through that. But in general, what we're seeing is proportion of different proteins coming from our main raw materials. So over the total analysis with more than 100 beers, we've found almost 2,000 individual proteins in beer. And a lot of these were coming from yeast. And certainly where they were using Belgian-style ales, lambic styles, where you have a lot of influence of yeast, that was really sort of potentially biasing the data. But proteomics allows us to really explore what's going on, not only just in the malting and the brewing process, but what's in finished beer and the variation we can see in finished beer. Certainly, we can't talk about any omics without mentioning metabolomics, and this is some work that the Colorado State University has been doing, and now we're getting involved with them as well, looking at the effects of variety on malt flavour. And I'm sure in the craft industry, we've heard them talking about this. What is the effect of barley variety? Old varieties like Maris Otter or Golden Promise, they're saying we have a distinct flavour. How much of that is actually where the barley was grown? So there's an environmental effect, terroir, if we want to use that sort of terminology. How much of it is in the malting process? We know that if you use a large box maltings versus a floor maltings, that we see flavour differences based on the processing. And certainly brewing style will influence all of that, hopping rates, the beer style. And we're currently working on a project of malt age. So when you buy your malt, how old is your malt? How has it been stored? So all of these things can influence flavour. So that's what we're currently working on. And again, distribution of compounds. This is work that Hermione Bettenhausen's done as part of her PhD at Colorado State. And again, we're seeing literally hundreds of compounds that influence flavour. These are metabolites from malt as well as beer, and lining those metabolites, what's coming from malt, what ends up in beer, and then what influences our sensory profile of that. So again, this is one of these omics technologies that's really helping us to dig much deeper into quality and how variety, growing region, malting process can influence that flavour. So that's it for me today. Certainly, you're welcome to reach out. We have a fairly broad educational program. as well as we're open to collaborative research. There are my details there. You're welcome to reach out any time. And of course, we've got to be on some sort of social media platform, so my students tell me. So there's some Twitter accounts. Apparently we have an Instagram, but I'm not quite sure if I know what Instagram is, and I'll probably cop heaps of flack for that, but that's okay. I don't mind. And that's it for me.